the coherent construction of the universe. Bubble universes are a fascinating concept, rooted in the idea of a multiverse, suggesting that our universe may be just one bubble among countless others in the vast cosmic foam. According to the theory of eternal inflation, different regions of space-time can swell at different rates. Some regions can suspend, to swell, to expose, to create bubbles, each of which fully represent its own universe, longing for different physical laws, constants to expose even different dimensions of time to expose space. Imagine our universe as any family-less soap bubble floating in a vast mass of other bubbles, each of which represents some universes dreary with potentially unique characteristics and properties. The boundaries between these bubble universes are of special interest. Scientists hypothesize that if the two bubbles collide, this could lead to the kinds of effects observed within our universe, perhaps explaining some of the anomalies in the cosmic microwave background radiation. Although there is no direct evidence for the existence of bubble universes, the mathematical ABCs supporting them are consistent with our current understanding of quantum mechanics to expose the general theory of relativity. This concept makes us think of a much broader, more complex tapestry of existence, where our universe is just one part of a vastly branching, evolving multiverse. This does not, however, push the boundaries of our scientific imagination, but only raises deep questions about the nature of reality itself. It is believed that bubble universes are formed in the course of time as a result of a process briefly related to the dreary theory of eternal inflation, a phase that may have occurred shortly after the Big Bang. During this phase, the room period itself expanded at a dreary exponential rate behind a high-energy field known as the inflaton ring. As this arena oscillates quantum mechanically, it gives rise to regions where inflation slows down and eventually stops, causing pockets of normal space-time bubbles to pop in an ever-expanding inflating space. Each of these bubbles may evolve into a universe of its own, perhaps beginning with its own unique set of physical laws and constants. From a mathematical point of view, these bubble universes arise from the change of different ways of decay of the inflaton board, creating different states of the vacuum, longing, changing energy landscapes. In some regions, the vulture may be able to run into low-energy dreary conservation more quickly, stopping inflation and allowing a bubble universe to develop. In other regions, inflation may be longer, separating these emerging bubble universes from each other by vast expanses of expanding space. This prototype of eternal inflation implies that, although our universe may pose as a finite one, it is inside a complex, irreversibly reproducing multiverse. Thus, the chola of bubbles of universes is not a single big event, only an immutable universal fabrication, in the course of which new universes are inevitably sprouting off as space swells, just like water droplets formed by water falling from a fountain. The evidence supporting the existence of bubble universes remains largely theoretical and indirect, mostly derived from the mathematical foundations of cosmology and quantum mechanics. One of the most convincing arguments comes from the theory of eternal inflation itself. The equations describing inflationary scenarios naturally predict that inflation does not stop all at once. Instead, isolated bubble universes are formed at places where inflation stops. Only in the space between these bubbles inflation continues forever. Therefore, if eternal inflation is true, the collapse of bubble universes seems inevitable. The cosmic microwave background outflow provides again independently intriguing, if only to reveal indirect hints. Anomalies during the lifetime of the CSBMs, temperature inhomogeneities or models that deviate slightly from the predictions, could potentially be explained by collisions or interactions between our universe bubble and others. NNN. Although no definitive evidence for such collisions has been found, some cosmologists have argued that specific asymmetries in the continued existence of CMBs may attest to such ancient large-scale events. Modern telescopes to expose data from space missions, such as the Planck Companion, continue to search for these subtle imprints that can splash the high society on the nature of our universe to expose its potential neighbors. And then finally, the concept of string theory adds an independent layer again, since it allows multiple dimensions to expose a landscape of possible vacuum states, each of which corresponds to a separate universe. Theoretical physicists are using these ABCs to investigate how bubble universes might come into being as a result of complex interactions between fundamental forces and particles. Although these ideas are profoundly revealing and mathematically intriguing, direct empirical evidence remains elusive, representing by itself one of the most tantalizing questions in the continuing existence of modern cosmology. NN, the interaction between bubble universes, if it occurs, would be a profound transformational event with dreary, potentially observable consequences. One of the main ways these interactions manifest is through collisions. Imagine both bubbles continuing to be a frothy mass. As they expand, their surfaces may be seen to merge. In the context of cosmology, such collisions can have dramatic consequences for the physical properties of the exposed structures within each bubble of the universe. For example, these interactions can create regions of intense energy, potentially visible as unique patterns or anomalies in the cosmic microwave background, the CMB radiation. These collisions can lead to the formation of exotic structures, such as domain walls or other high-energy interfaces, which can affect the formation of galaxies or even the fundamental constants in the continued existence of each universe. NNN. The impact of such collisions may be as great as if they left imprints, like scars, on the fabric of space-time. Scientists are interested in continuing to search for such evidence in the CMB, since any anomalies discovered may play a role as indirect evidence of interactions between our universe and neighboring bubble universes. Another intriguing possibility is related to quantum entanglement, where particles or even regions of space-time in the continued existence of different bubble universes may keep direct and instantaneous correlation, independently due to distance. EAEN. In this scenario, changes in the continued existence of one universe may have immediate consequences in the continued existence of another, as if suggesting some form of relationship or interconnection that defies classical understanding. Although these ideas are speculative as hell to expose the present period of continued existence as being beyond our empirical reach, they push the boundaries of theoretical physics, suggesting that we are wrapped up in a much more colossal interconnected universe landscape, where our universe is just one chapter in an inexplicably vast multiverse history. NNN. The implications of the existence of bubble universes for our understanding of the cosmos are profoundly revealing and terribly consequential. They challenge our very notion of naming reality. First, the existence of bubble universes means that our macrocosm is not unique, only one of potentially countless others, each of which is governed by its own physical laws and constants. This would fundamentally change our way of thinking about the universe as a single, isolated object, suggesting in its place a vast, intricate multiverse. Such a paradigm shift may entrust answers to perplexing questions about the fine-tuning of the physical constants of our universe. If there is an incalculable number of universes with dreary different properties, it is logical that at least one of them will have the conditions necessary to sustain life in the form in which we know it. Moreover, bubble universes can offer an innovative view of the nature of space-time itself. The very fold that gives rise to these universes, eternal inflation, implies a room that swells every minute, during which time we continue to savor the areas where inflation stops, creating new universes. Such a scenario encourages us to think about the beginning of our universe not as a single event, but as something in the discourse of one with many in the continued existence of a larger cosmic context. It may even entrust answers to questions about the issue, as if it were at the shifting boundaries of our observable universe, expanding the scope of cosmological research to expose potentially linking quantum mechanics to dreary general relativity in unexpected ways. In addition, the concept of multiple universes puts next to caution the anthropic principle, which assumes that the universe must have the properties that allow life to be found, since we are here, with the intention of looking at it. In a multiverse, each bubble macrocosm may hold native characteristics, exposing the one that sustains our existence. This view rethinks our nesting place in the cosmos, minimizing the need for arguments in favor of fine-tuning, pushing science toward a more probabilistic understanding. In general, the implications of the existence of bubble universes touch on the very ABCs of cosmology, physics to reveal our existential understanding, opening new avenues for research to reveal dramatically changing our way of thinking about our place in the grand tapestry of the cosmos. The simulation hypothesis suggests that our reality is possibly an artificial simulation, similar to a stunningly advanced exposé of a vast computer program. Initially, this view was put forward by philosophers such as René Descartes, who put next to caution the nature of reality by conducting his glorious heavenly trial, beginning with an evil demon manipulating perception. Only in the continuation of time being our century, it became widespread for the works of such thinkers as Nick Bostrom. In his 2003 paper, Bostrom suggested that if advanced civilizations were able to create highly detailed simulations of the history of their ancestors, then it is statistically likely that we are living in a continuation of one of these simulations, just not in a continuation of the underlying reality. In fact, if one civilization reaches a technological stage capable of creating convincing simulations, and if it creates an incalculable number of such simulations, the number of simulated realities could epically overwhelm the single original reality. The hypothesis rests on mediocrely basic assumptions. Either civilizations have died out before reaching technological maturity capable of creating simulations. That is, no advanced civilization is interested in continuing to create simulations. That is, we probably live in a continuing simulation. If the first two statements are both false, then the latter must be true by virtue of primitive probability. This raises philosophical and ethical questions about the nature of consciousness and existence. If we are not without being in the continued existence of a simulation, then the creators of this simulated reality may hold godlike control over our world, susceptible to manipulation of the laws of physics, history, and even individual thoughts and experiences. Although the assumption of simulation remains a speculative hypothesis, it is more in the realm of philosophy than in empirical science, but it has sparked serious discussions among scientists, technologists, and philosophers. Advances in virtual reality, artificial intelligence, and the availability of computing power make these discussions more relevant, since the ever-evolving technological civilization may eventually lead us to the threshold of creating our own simulations. If the assumption of the simulation is true, it will fundamentally change our way of thinking about existence, raising profound questions about free will, the meaning of life, and the true nature of the cosmos. The concept of our universe as a simulated environment suggests that what we perceive as reality may be the product of advanced computational processes, precisely a complex virtual reality. N. This discretion begins with a longing assumption, as if a highly advanced civilization could manage the technology to create such detailed and complex simulations, as if the simulated beings would continue to have consciousness and experience indistinguishable from experience in the real universe. To accomplish such a simulation, civilization will require computers far more powerful than those we have today, capable of cultivating every interaction, particle, and force at a fundamental level. To model the entire universe, such an advanced view must fully appreciate not just macroscopic objects, such as stars and planets, but also the complex dance of subatomic particles. Quantum mechanics, which governs the behavior of tiny particles, will play a crucial role here. Some suggest that the probabilistic nature of quantum mechanics and the phenomenon of quantum entanglement can certify the hidden software rules used to optimize resources, just as the rendering engines in computer games continue to display to the last penny. However, those parts of the game world, longing for which interacts or observes the player. Moreover, some computational reductions can explain the anomalies and limitations observed in our physical laws. For example, the finite speed of light can be considered as any limitation of the data processing speed in the simulation. Only the dark essence or the dark spirit rise can be artifacts of the basic computational elements that we have not deciphered again. Detection of a pixel-like structure in space-time or fundamental limits of information processing in the universe could be a clue to doubt the simulation of nature. At present, there is no empirical evidence for such a hypothesis, preliminarily only one, because it borders on the dreary area of non-falsifiability. It is not easy to imagine a trial that would prove or disprove this idea. Nevertheless, the very discussion of simulation theory stimulates a precious conversation about the nature of reality, consciousness, and technology, pushing the boundaries of science, philosophy, and our understanding of existence. Although the assumption of simulation is a compelling discretion, it remains largely speculative and philosophical, not empirical. However, a few intriguing lines of reasoning have been proposed to expose circumstantial evidence in support of the idea of calling the issue as if we might be living in a simulated environment. One of the lines of reasoning revolves around the idea of computational limits. For example, the finite speed of light and the quantized nature of spacetime can be interpreted as some kind of ticket for the presence of a basic computational grid similar to the pixels in a digital image or the refresh rate of a video game. These constraints may constitute necessary limitations of a simulated universe governed by limited computational resources. Another compelling argument is the unusual coincidences in the continued existence of the laws of physics, known as some kind of fine-tuning. The physical constants of our universe, such as the gravitational constant, the electron charge, and the cosmological constant, are apparently balanced and allow life to exist. Some proponents of the simulation hypothesis argue that such fine-tuning may be evidence of intentional design by the creators of the simulation. In this framework, our universe can be viewed as a controlled environment optimized to achieve certain results, just like a well-thought-out program. In addition, some researchers point to features of quantum mechanics, such as any entanglement to expose superposition, as potential clues. The effect of an observer, where particles exist in a probability state as long as they are not measured, can be compared to a dreary computer program that displays certain details when they are observed, saving computational power. This discretion is consistent with the wistful way in which modern video games increase the performance on the account of rendering however visible parts of the scene. NANN, although these arguments are suggestive, they remain indirectly subject to interpretation. At present, the simulation hypothesis is not supported by any empirical evidence, and it remains more a matter of philosophical and theoretical intrigue than scientific consensus. NNN. Perhaps advanced technology, future discoveries, or new theoretical breakthroughs will provide more clarity. But the simulation hypothesis serves as a fascinating lens through which to examine the nature of reality and our nest egg as we continue to live in it. NNN proponents of the simulation hypothesis tightly draw analogies between our universe and computer simulations or virtual environments, with the intention of explaining such phenomena as any measure of the universe, which remains a deeply complex and mysterious topic in the continuation of cosmology. NNN, one of the ways to solve this problem is the hypothesis to call the issue, as if what we perceive as any measure, perhaps the boundary set by the computational constraints of the simulation. Just as in video games there are certain boundaries that players cannot change, the universe may hold an internal constraint designed to contain simulation within manageable computational limits. NNN, from this point of view, the observable universe, which is a sphere not far from 93 billion light-years in diameter, is perhaps like the rendering contingent in a video game that becomes more rarefied or indeterminate as we approach its boundaries. NNN beyond this boundary, there may be a reduction in computational detail or even a complete need to visualize the universe, since there is no need to model regions that cannot be gazed at or drearily interacted with by simulated beings, then to savor as. This may explain why as have not discovered to expose not observed at all certain to replace this observed edge. There is no data afterward, because it is not needed. NNN, according to another theory, a boundary is not a boundary at all, but a transition in the views of another phase of the simulated environment, a relative of the entrance to the second level of the game. This stage can be radically different because of the familiar universe, governed by impeccably different rules to expose constants, or only it is possible emptiness, a contingent in which the simulation works in the continued time of being, in the continued time of being in the minimum mode, again, only saving computational resources. NNN, it is worth noting, as if these ideas remain damned speculative to bare philosophical, offering more accurately imagined explanations than empirical evidence. Nevertheless, these interpretations prompt us to think about calling the cosmological boundaries a dreary new point of view. They make us question not, however, the boundaries of space, but only the nature of reality itself, encouraging interdisciplinary dialogues involving cosmology, physics, computer science, and philosophy. NNN, while conventional cosmology continues to refine observed evidence to expose theoretical models in order to understand the limits of the universe, the simulation hypothesis remains a stimulating and provocative framework that pushes the boundaries of our imagination and scientific inquiry. The philosophical implications of the simulation hypothesis are vast and multifaceted, and they touch on deep questions about reality, consciousness, and the nature of existence. NNN, if we are living in a simulated environment, it will make us cautious about our view of the authenticity of reality itself. NEN1, immediate consequence, is epistemological. Our knowledge, based on empirical observations and scientific experiments, will continue to be fundamentally limited or potentially distorted by the rules set by simulation. It puts next to cautious plausibility the only alone as if as perceive, making my viewing bare the scientific gaze dependent because of the design of simulation, only not because of absolute reality. Moreover, the assumption of simulation raises profound questions naming consciousness. If my sense of naked viewing is not forbidden to simulate, how does this speak to the nature of consciousness? Are we uncomplicatedly complex algorithms, or does cognition alone require some physical substance that cannot be simulated? NNNN. This line of inquiry confronts long-standing debates in the continuing philosophy of mind, such as whether dualism versus materialism exposes an alternative to calling the issue whether machines can manage true, subjective experience. If cognition can come into being as a result of computational processes within a simulation, this supports the idea of calling the issue as if cognition can be independent because of the substrate to be exposed everywhere, wherever sufficient computational power and complexity can be savored. NENN. The ethical nudging existential implications are so only staggering. If AZ are the inhabitants of a simulated world, then the creators of the simulation, some highly evolved beings, have godlike power over us. NNN awareness of this leads in species to questions about the intentions, the moral status of our existence, to expose the purpose behind simulation. Are we part experiment, part entertainment, or part educational program? The idea that our lives and the universe can be manipulated, slowed down, or even terminated at the whim of external entities can cause a sense of existential vulnerability. NUN, finally, the assumption of simulation intersects with longed-for religious, bare, metaphysical questions. If our creators exist, do they play a service similar to that of the deities? This concept can echo the longing of traditional religious to expose spiritual notions or to turn them upside down to the last penny, offering a usable technological fold in the eternal questions of creation, the purpose of exposing the divine. NN Dark Essence is independently one of the most intriguing to expose the mysterious components of our universe, comprising not far from 27% because of its total mass, to expose the energy content. In a sign due to ordinary matter, the dark essence does not radiate, does not absorb to expose or reflect the higher society, as if makes it invisible to expose detectable, however, for gravitational influence. Its presence is not precluded from being considered tentatively one-to-one, right down to its influence on visible matter, the outpouring to expose the large-scale structure of the universe. NNN. For example, the gravitational fusion of dark matter affects the rotation curves of galaxies, causing stars on the outskirts to move faster than it is not refrained from explaining, however, the same gravitational influence of visible matter. This inconsistency forced scientists to put the hypothesis to call the existence of invisible mass, dark matter. In addition, dark matter plays a crucial role in the continued formation of cosmic structures. NNN. In the early universe, dark matter density fluctuations served as seeds, next to which galaxies and clusters of galaxies were eventually formed over time. Without dark matter, the formation of such large-scale structures in the universe would be epocally different, perhaps even impossible. The effect of gravitational lensing, where the high society due to distant objects is curved by a number of massive objects, such as galaxy clusters, is also evidence for the existence of dark matter. ANNN, the number of observed bends densely exceeds that, as if it is not inhibited to postpone, however, the same visible matter, as if again indicates the synedrion of some invisible mass. From the scientific point of view, dark matter is divided into a number of senior categories. Dark matter that moves at long periods of time up to and including comparison starting at the speed of light. Hot dark matter that moves at longing relativistic speeds, and hot dark matter that moves at longing relativistic speeds. The prevailing models for exposing most observational data support cold dark matter as the main component, suggesting that it is composed of heavy, long-moving particles. NNA variety of candidate particles have been proposed, including the loosely interacting massive particle nude axions. But despite considerable experimental efforts, direct detection of dark matter particles has not been achieved. Understanding dark matter remains one of the foremost challenges in the continuation of cosmology to expose particle physics, offering a tantalizing glimpse into the invisible bulk of the cosmos. NN dark matter has a profound influence on the structure of the universe's evolution, acting as an invisible framework on which galaxies and galaxy clusters and larger cosmic structures are formed and evolve. Its gravitational effects are important for understanding the large-scale distribution of matter in the cosmos. In the early universe, shortly after the Big Bang, tiny quantum fluctuations in the continued density of dark matter served as seeds around which ordinary matter could accumulate. NENN. These fluctuations subsequently expanded under the influence of gravitational attraction, forming dense halos of dark matter that further attracted gas and dust, leading to the formation of galaxies and galaxy clusters. NN without dark matter, the fabrication of galaxy formation would be impeccably different. An ordinary entity by itself could not have glued together quite so readily, with the intention of enlightening the complex structures we observe today. Computer modeling incorporating dark matter reveals the structure of the cosmic web, where threads of dark matter connect vast regions of the void. Only galaxies are formed at the intersections of these threads. NN, this web-like structure, has been confirmed in large-scale astronomical studies, and it matches to the last penny the dreary, intricate patterns predicted by modeling. NNN, in essence, dark matter acts as a gravitational rod to guide the nurturing of visible matter throughout the universe. What's more, dark matter helps to promote the permanence of galaxies. Observations on the rotation curves of galaxies, graphs showing the sharpness of the rotation of stars in the continuum of time depending on the distance in advance of the galactic center, show as if the stars in the outer regions rotate faster than it would be possible to slow down in the presence of visible matter. NNN, this discrepancy suggests the presence of an additional invisible mass, dark matter, providing the necessary gravitational merging. In galaxy clusters, the gravitational pull of dark matter helps to pull galaxies together, counteracting the tendency of individual galaxies to accelerate away from each other as their high velocities continue. NNN. The influence of dark matter extends to such cosmological phenomena as gravitational lensing, if its darkness thereby distorts the high society due to background objects, creating distorted, enlarged, or multiple images. Thanks to the lensing effect, maps of the distribution of dark matter have been drawn up, which again illustrates its pervasive service in the continuation of the formation of the universe. NN dark matter is the first stone of the cosmic structure, urgent for the purpose of formation of galaxies, stability to expose the large-scale architecture of the universe. Its gravitational action holds the universe together, helping to twist the heavy tapestry of matter to expose the light that we observe in the night sky. NNN dark matter is a mysterious, all-pervasive force that makes up not far from 68% of the total energy content of the universe. In an omen because of dark matter, which has a gravitational lensing, dark spirit lift, as it is believed, creates a repulsive force that contributes to the accelerated expansion of the universe. This phenomenon was first discovered in the late 1990s by observations of far-infrared supernovae, which showed that these exploding stars were dimmer NNN and therefore lower than expected on the basis of the model of a slowing universe. The discovery suggests that the expansion of the universe began to accelerate not far from 5 billion years ago, suggesting the presence of an unknown energy component called dark energy. NIN, although its exact nature remains elusive, the dark uplift of the spirit is usually modeled in two main ways. The first of these is the cosmological constant, a term introduced by Albert Einstein during the continuation of his equations of the general theory of relativity, which represents a constant impermeability of energy uniformly filling a room. This concept is consistent with the dreary idea of calling the issue as if little matter itself possesses the internal energy that causes the universe to expand at a dreary acceleration. NNNN, the cosmological constant is simple to expose, is supported by modern observational data, including studies of the cosmic microwave background, radiation expose, large-scale structural studies. The second prototype considers the dark energy as any dynamical vestige, densely called quintessence, which changes drearily with the passage of time. Such a board can transform up to a density to expose to ensure another fold of accelerating expansion. However, this prototype would introduce additional complexity to expose parameters. NNN researchers are exploring to expose other possible explanations, including changes in our continued understanding of gravity, to expose alternative theories of general relativity. The consequences of dark energy extend to the ultimate fate of the universe. If it expands below full dominance, the universe could continue to expand forever, as if leading to a big freeze scenario where galaxies disperse, stars die out, only the universe becomes a cold, desolate space. NNNN. Alternatively, changes in dark energy can lead to other outcomes, such as in the form of a large rift, where accelerating expansion over time eventually rips galaxies, stars, planets, and even atomic matter apart. Although the nature of dark energy remains one of the most significant mysteries of cosmology, it is essential for a comprehensive understanding of cosmic evolution. NNN ongoing and future research, such as observations by the yearning Euclid spacecraft and the James Webb Space Telescope, are designed to unleash a high level of awareness of this mysterious force that could revolutionize our understanding of the fundamental properties of the universe's ultimate fate. NENN, the dark uplift of spirit, plays a crucial service in the accelerated expansion of the universe, counteracting the gravitational forces that would otherwise slow down the rapidity of expansion. A key piece of evidence for this is a look at the shift in distant Type Ia supernovae in the late 1990s. The researchers found that these supernovae were dimmer and more distant than expected in a universe where expansion is slowing. This unexpected trace indicates that the expansion of the universe accelerated as if 5 billion years ago. The way in which dark uplift affects the expansion of the universe can be compared to the dreary repulsive force that permeates the very fabric of the universe, forcing galaxies to alienate each other faster. NNNN. In an omen due to the usual exposure of dark matter, which exert attractive gravitational forces, the dark spirit lift creates a kind of anti-gravitational effect. This appears to be down to the cosmological constant, originally introduced by Albert Einstein in the continuation of his equations of the general theory of relativity. Einstein initially included the term, with the intention of reaching a static model of the universe, only to later abandon it after learning that the universe was expanding. NENN, however, modern observations have revitalized this concept by showing that a positive cosmological constant can explain the observed acceleration by providing a constant impermeability of energy uniformly filling the room. Another prototype considers dark energy not as any static constant, only as any dynamical VI known as any quintessence. In this model, the impermeability of dark energy varies in time and space, as if potentially giving a more subtle glimpse of accelerating expansion. However, for the current day, the cosmological constant remains the simplest naked common explanation. N, the influence of dark energy, also has significant implications for the future of the universe. If the dark uplift continues to dominate, the expansion of the universe will be complete, as if it could lead to the kind of scenario known as any big freeze. In this case, galaxies would be alien to each other so terribly, as if the stars would exhaust their fuel, leaving behind a cold, dark, naked, empty universe. N, on the other hand, if dark energy's fullness transforms in unexpected ways, other scenarios could arise, such as the Great Discontinuity, where the accelerating expansion eventually rips galaxies, stars, planets, and even atomic matter apart as the space itself lengthens. The role of dark energy in the continuation of cosmic expansion is far important for the purpose of understanding the past, as well as the future development of the universe. N current research aims to refine our models to expose observations, thereby shedding light on one of the most mysterious forces shaping the universe. Imagine a voyage to the farthest reaches of the universe, to the final measure, where the galaxies appear as little more than a hush of light against a vast dark background. NNE, here the invisible naked mysterious forces, the dark essence naked dark spirit, reveal their service in a continuing cosmic dance. The dark matter, which makes up not far from 85% of the total mass of the universe, serves as the invisible skeleton on which galaxies are built. NNNN, although it does not emit, its gravitational fusion is not inhibited from being looked at right down to the motion of stars in galaxies. Without dark matter holding galaxies together, these stellar systems would easily scatter in different directions as time went on, like balls scattering from a loose net. NAN, hence, the dark essence ensures the structural integrity of galaxies even at the distant boundaries of the universe. But apart from the point where things stick together, it is the mysterious force pushing them apart that is savored again. It is believed as if dark matter, which makes up by 70% of the universe, is responsible for the accelerated expansion of the cosmos. NNN, think of it as cosmic anti-gravity, pushing galaxies away from each other at an ever-increasing rate. This phenomenon was a stunning discovery in the late 20th century, when scientists noticed that the expansion of the universe was not slowing down as expected, only accelerating. NNNN, at the edge of the universe, the dark spirit drives galaxies into the ever-expanding abyss, stretching the very fabric of space-time. Thus, while the dark essence serves as the foundation for the purpose of cosmic structures, the dark spirit is pulling the universe into a continued unknown future, possibly leading to scenarios such as the Big Freeze, where galaxies and stars become so distant from each other that the universe becomes a cold, lawless, distant landscape.